Welcome back, guys. Now that we are done with interconversion from decimal to all the other three number systems, it's time that we look upon how to convert from octal to binary, octal to hexadecimal, hexadecimal to binary, binary to hexadecimal, and so on. First of all, we'll look at how to convert from octal to binary. So the first step in this conversion is that convert each octal digit to a three-digit binary number. The octal digits may be treated as decimal for this conversion. This means, say suppose you have an octal number that is 25, obviously base 8 because it is octal. Now you have to convert this particular octal number into binary. So what you will do is consider this 2 to be in base 10 and this 5 also to be in base 10. So we have 2 base 10, 5 base 10, although the entire number is obviously base 8. In the next step, what you'll do is you will convert this 2 into its equivalent binary form. And we know that the equivalent binary form of 2 is 010 or rather 10. Now we have written it as 010 because it is octal. And for octal, we always make groups of 3 because its base is 8 and 2 to the power 3 is 8. So we always make groups of 3 in octal. So over here we have 2 as 010 and 5 as 101 because 101 is the binary equivalent of 5. So we have covered the first step, that was convert each octal digit to a 3-digit binary number. So we have already done that. This 2 has been converted to 010 and 5 into 101. Now in the next step, that is the last step obviously, combine all the resulting binary group into a single binary number. Over here we have two binary groups, that is 010 and 101. So we can combine it to give 010 101. So we have just combined this one, nothing special. Now one thing to notice is that we have this stray 0 at the leftmost position. Now if you get any scenario like this, you can always omit all the zeros if they occur at the leftmost position. So over here we have 0 1 0 1 0 1. So we can always omit this 0 which is at the leftmost position because it does not make any sense after all. And therefore we get the shortened number as 10101. Let's take a look at this example. We have 537 and we have to convert it into binary. So according to the first step, we first convert each octal digit, that is 5, 3 and 7, into its equivalent binary form. So the binary of 5 is 101, 3 is 011 and 7 is 111. And now as per the second step, we just combine them. And after combining we get 101, 011, 111 and that is your equivalent binary number. That's quite simple. Now let's take a look at this one more example over here. We have 276.435 in octal number system. To convert it, we have again 2 is written as 010, 7 as 111, 6 as 110. We put a decimal point over here. Then we have 4 whose equivalent binary is 100, 3 is 011 and 5 is 101. Now we combine this entire thing and we get 10111110 dot 100011101. Now take a note that I did not write this particular 0 over here because I have already said earlier that you can always remove any stray zeros over here. But just in case there is a stray 0 before this one, say suppose if we had over here 010, then in that case we cannot remove that 0 because it is after the decimal. Now had that 0 been like 1010, that means after the decimal point, if we have any zeros at the rightmost position, then we can omit those zeros. These rules are similar to what we use in normal mathematics, so you don't need to worry about it. Now we see how to convert from binary to octal. In this process, what we will do is, in this first step, we'll divide the binary digits into groups of 3 starting from the right hand side. So actually this process is just the opposite of what we did over here. So let us take a look at this example. Here we have a binary number 10101. So starting from the right hand side, we will make groups of 3. So the first group we have is 101. We write the first group here 101. In the next group, we have only 1 and 0. That means we do not have 3 digits. So what we will do is we will just place one 0 out here, because placing any 0 at the leftmost position does not make any change to the binary number. So we write it as 010. Now we clearly have groups of 3. Convert each group of 3 binary digits to one octal digit. What we do is, now that we have groups of 3, we will just convert this particular group into its equivalent octal and this group into its equivalent octal. So 010 is essentially 2 in octal number system and 101 turns out to be 5. Now we just combine this individual numbers to get the entire octal number. So we get 25 base 8. Let's take a look at another example. Over here we have 10 10 11 11 another 1. So over here also, starting from the right hand side, we make groups of 3. So the first group is 111, we have 111. Next group is 011, we have 011, and the last group being 101. So we have 101. Now this 101 is octal 5, 011 is octal 3, and 111 is octal 7. Therefore, we combine these 3 octal digits into 1 to get the entire octal number. Thus, we get 537 in octal number system. And in this example, what we have is 10111110. Here also, we'll do the same thing. We'll just make groups of 3, and for this part also, we'll make groups of 3. But take a note that if we have anything after this decimal, then we will consider group of 3 from left hand side, unlike in this one. Anything before, if we had anything before the decimal, we used to make group of 3 from the starting from the right hand side. That means starting from this 0. So we get 110 as the first group, 110 is the first group, next one is 111, and then we have 10, and we place another 0 in the front to get 010. But for this decimal part, what we will do is we will start making group from the left hand side. So we get 100 as the first group, then we have 011, and then is 101. Now that we are done with grouping, we will just convert it into the equivalent octal. So 010 is 2, 1117, 110 is 6. We put the decimal and then the same thing 4, 3 and 5. So this is the entire octal number. Now we take a look how to convert from hexadecimal to binary. It's pretty much the same. The only difference is that in octal to binary, we took groups of 3. In hexadecimal to binary, we'll take groups of 4, because the base of hexadecimal is 16 and 2 to the power 4 gives 16. So we will take 4-digit binary numbers. Let's take a look at this example. We have 15 base 16. So we will first convert this 1 into its binary form. So we get 0001 and 5 is 0101. Now we merge this entire thing into 1 to get 0001 0101. We can obviously eliminate these 3 stray zeros. Therefore, the equivalent binary number is 10101. Probably this example must make things clear. Over here, we have 53D. Binary equivalent of 5 is 0101. Binary equivalent of 3 is 0011, and the binary equivalent of D. Now, looking at the chart, we have D, and decimal equivalent of D is actually 13. So we represent 13 in binary form. So 13 in binary is 1101, because this one is 2 to the power 3, this is 2 to the power 2, and this one is 2 to the power 0. So 2 to the power 3 is 8, plus 4 12, plus 1 13. So the binary equivalent of D is 1101. Now we merge this entire thing and we get 101 00111101. Take a note that we have removed this stray 0 over here. In this example, we have a decimal point and the number is 2b6 dot rather point 4f5. So first of all, we just write the decimal binary equivalents of these digits to get 0010, 1011, 0110, point 0100, 1111, 0101. We remove the stray zeros as usual to get 1010110111 dot 01 and so on. So this is the entire binary number for this particular hexadecimal number. Now we see how to convert from binary to hexadecimal. So in this conversion, this one is actually similar to how you converted from binary to octal. In binary to octal, you made groups of 3. From in binary to hexadecimal, we will make groups of 4. So if we have the number as we're using the same example again actually. If we have the number 10101, so we will start making groups of 4 starting from the rightmost side. So starting from the right hand side, we get 0101 as the first group, 0101 is the first group, and this is the only one that remains. So what we will do is we'll just concatenate 3 zeros before this one. That makes no difference. Thus we get the number as 1, and obviously the decimal equivalent of 0101 is 5. Now we just merge it to get 1 5, that is 15. Notice the fact that this 1 5 does not actually mean F. It is not F. Let's take a look at this example. This would clear the concept. Here we have 101 00 111101. Now we start making groups of 4 starting from the right hand side, and we get this. Now 0101 is 5, 0011 is 3, this 1101 is D. Therefore we get 53D base 16 as our hexadecimal number. Over here we have written this D because we had the binary group as 1101. Now this 1101 actually stands for D, unlike in this case. Over here we had two different groups. That's why we did not write it as F. So similarly we have proceeded in this example as well. You can take a look. We just make groups of 4. We put the decimal point at the right place and then convert it into its equivalent hexadecimal form. That is all for number system interconversion. In the next video, we shall take a look at assembly language, high level language, compilers and interpreters. Thank you.